Today we're going to take a look at specific heat, specifically the specific heat of a liter of water. What we're going to do is take 1,000 milliliters or 1 liter of water. We're going to pour it into this glass beaker and we're going to warm it using an immersion heater. This is the same kind of thing that you might use in a cup of water if you wanted to make some tea in your office, or if you wanted to warm a cup of soup and you didn't have access to a microwave or a stove top. We're going to place the immersion heater on the edge of the beaker so that we can have it heating up the water. And we're going to keep track of the temperature of the water using a temperature probe. All of this is going to be monitored using Logger Pro. And after we've heated the water to about a temperature of 50 or 60 degrees Celsius, we're then going to turn the immersion heater off and let it cool. In order to ensure that all of the energy from the immersion heater, or as much as possible, is actually going into the water, we're going to insulate the beaker using this foam. After we've allowed the water to cool for a little bit, we're going to actually remove the lid from this foam container so that we can then watch to see how having the entire thing insulated versus removing the lid might actually change how the water cools overall. You won't be able to see this on the inside once it's insulated, but what this system will look like on the inside is like this. We'll see the heater in there and the temperature probe and the thermometer in there, keeping track. So now we'll get this set up. Once the temperature probe comes to equilibrium with the water, we'll plug in the immersion heater and begin the heating process. So now we are collecting, and we will plug in our heater. And observe the system. So now that we've reached our target temperature, we're going to remove the immersion heater so that we can watch the system begin to cool. And we'll unplug it and then remove the heater. Now that we've observed it cooling for a little bit with the lid on, let's remove the lid and see what type of a difference that makes. Finally, since we can see that the cooling is a very slow process, we will remove all of the insulation and see how it cools without insulation at all. That did require a temporary removal of the thermometer. Now that we have our data, let's take a look at what all of it means. This is a graph of our temperature versus time for the water, along with the power output read by the watt meter for the immersion heater. So if we take a look at simply the heating portion of the graph, the upward slope, what we actually see is that we had a temperature change of about 30 degrees Celsius over the course of 20 minutes. Um, so if we apply the equation for heat, mc delta T, we have a mass of a kilogram. The specific heat of water I'm using as 4,200 joules per kilogram Kelvin or per kilogram degree Celsius. I'm rounding it because we're using tap water. The specific heat of water changes with impurities. If you add salts, it lowers it. If you add other impurities, it tends to raise it. So I'm rounding it to 4,200. And we put in that temperature change of 30 degrees Celsius or 30 Kelvin increase in temperature. We get a measurement for heat of 126 kilojoules or 126,000 joules. If I divide that by the time that took, 1,200 seconds or 20 minutes, we find a power rating of about 105, 106 watts. Now, if I look down at our power graph and take the average power output for the entire 20 minutes, we see an average power of 113 watts. So this is with insulating everything. We're pretty efficiently transferring as much energy as we can from the heater into the water. Now, if we take a look at the cooling sections of the graph, it doesn't immediately look like there are any differences in what's happening with removing the heater, removing the lid, and then removing the insulation completely. But if we apply a trend line to the section where we removed the heater, we can immediately see that that line has a lower slope than the next segment of the graph where we don't have the heater or the lid inserted into the water. What we actually find if we look at the slope of that line is a slope of about 1.75 degrees per kilosecond, per 1,000 seconds. Now, if we look at the next section where we've actually removed the lid and the heat is also, or the heater is also already removed, we actually find a slope of 3.5 degrees Celsius per kilosecond or per 1,000 seconds. So it's actually cooling faster without the lid and about twice as fast without the lid versus with the lid on. And then if we go ahead and remove the insulation completely, we get a slope of 6.05 degrees per 1,000 seconds or per kilosecond. So insulation is absolutely a factor. So in conclusion, we've taken a look at the heating of water using an immersion heater. We've worked to get all of the calorie output, all of the energy output from the heater into the water by insulating the water and the beaker. We stirred the water so that we could evenly heat everything. Water is very high specific heat, so it's difficult to heat it evenly without keeping the water moving. We've taken a look additionally, not quantitatively, but more qualitatively at cooling and the differences that insulation can make along the way. So as a mom, wear your coats because insulation makes a difference in how you transfer your energy to your environment. Thank you.